Hello guys, welcome back to the second lecture of this practical building design series. In this lecture, we are going to create structural model for this 5-story under construction commercial project of my client. In our earlier lecture, we have already created the beam column plan for basement roof and ground floor roof. We are ready to start our structural modeling. So open the ETABS 2023 latest software. Here you can see a very slender and tallest residential building of New York, USA. Click on New Model button to start a new project. Here we will choose Build in Setting option. Units will be metric SI. Region for default materials will be India. As though we are not modeling any steel structure in this project, but it is a good habit to choose the right steel section database at the start of a project. Choose database as India. Steel design code for India is IS 800, and at last the code in which we are interested is concrete design code. For India, it is 456-2000. Choose it from the list and click on OK to proceed forward. Here earlier, what we used to do is take help of these grid dimension tools and story dimension tools to create reference point for creating the structural model. Now, as we have the correct beam column plan of our project, now we do not need the help of these tools. Here we only need to provide custom story data to ETABS so that it creates different stories with correct height for us. So choose custom story data option and click on edit story data button. Let's first provide correct name to our story. Starting from first story, name it basement. The clear height measured from basement floor to beam bottom level should be at least 9 feet 6 inch for commercial properties. We will be providing 2 feet deep beams, so the slab to slab height will be 9 feet 6 inch plus 2 feet, which will be equal to 11 feet 6 inch. This is the story height that you should provide in your projects so that it does not feel congested to customers when they enter into that space, as well as their hands does not touch the ceiling fan. Type 11 feet 6 inch in the height box for basement. Here you can see the height parameter says meter, but we can enter units in feet if we place this feet and inch symbol at the end of numbers. ETABS will automatically convert the value for us into meter. It is a cool feature of ETABS. Coming to second story, that is ground floor, name it ground. Generally, for a commercial building, ground floor plays an important role. It is the floor that attracts maximum rent for the clients. So we generally provide at least 12 feet clear ceiling height. We are considering 2 feet deep beams, so the overall story height will be 12 feet plus 2 feet, that is 14 feet. Enter the same in the height box. The story height above the ground floor follows the same rule of 9 feet 6 inch clear height. So the G+1 and above floor height will be 11 feet 6 inch. Name the third story as G+1 and enter height as 11 feet 6 inch. Same for G+2, enter the same. As this is a 5-story building project, so we will create more stories. To do so, right click on this G+2 story option. Here hover on to add story option, then click on keep existing story option. Here provide story height same as 11 feet 6 inch. We will create 3 additional stories. I will tell you why in few seconds. Rest of the settings will remain the same, so click on OK. Now name the story above G+2 and G+3. As we know that staircase will reach to the rooftop, so we always provide a roof room to staircase opening area to enclose it. So name it roof room. It is also called as multi-level. Generally we provide roof room a clear height of 8 feet plus 2 feet beam depth, so enter 10 feet height. Above roof room we always try to provide the water tank. So name the story as water tank. As of now, we are keeping the water tank story height as 1.5 meter. Later on, we will calculate the exact height of water tank as per the water requirement of this building. Make sure similar to option is set to none for all the stories. Click on OK button to save the story data into the new project. Here, we will be importing our own beam column plan, so we do not need grid help. So select blank object option and proceed forward. Now in order to check if ETABS have created the story level for us or not, click on this plan button tool from the top. Here you can see the entire story levels has been created by ETABS for us. We are going to create the basement roof first, So come to the basement level with the help of this down arrow tool. Now we are ready to import the basement roof beam column plan into our project file. For that, come to the file menu, then hover on to import option. Here select .dxf file for architectural plan option from this list. Here select the basement beam column plan DFX file. You can find this file in your download folder. Here the insertion scale will be in inch. We will be placing this beam column plan in basement story, so select it from the list. As we have already added the centerline plan for beams and walls in our AutoCAD file, so we will untick this add centerline option. Click on OK button to insert the plan into our project file. Here you can see the complete beam column plan has been imported. Let's quickly create columns and beams from this reference plan. For this, come to Model Explorer. Here shift to Display tab. Open the model window, then 3D view, then architectural layers. Here you can see the layers that we created in our AutoCAD plan. These layers will help us here to create columns, beams and walls quickly in ETABS. Right click on this column layer and add column object option. Here you can see in 3D viewport how quickly ETABS has created the columns for the entire floor plan. To see the columns in 3D, click on this extrude toggle button. Here you can see ETABS has created the circular as well as rectangular columns at precise location for us with 100% accuracy. Using these types of beam column plans, we have created complex floor plan structural model of G+12 story building in ETABS in our advanced mega course like this. For more details on advanced course, visit the Field Ready website. Now let's create the beams quickly. For beams, this time right click on the beam layer option and choose add beam objects. It will take 2 to 3 seconds. Here you can see nothing happens. But if you right click on this beam line, then you can see ETABS has created null lines for us. ETABS creates null line by default so that we can later on apply the beam properties as per our own wish. We are going to do the same. It's time that we define the material and section properties for this project. For this, come to the Define menu, then click on Material Properties option. Here, the by default material property for concrete created by ETABS is 4000 psi. We will change its property. So click on Modify button. Nowadays, we professional engineers are providing minimum M25 grade of concrete in all of our projects in India. You should also make this as your minimum RCC concrete standard. Change the name to M25. We know from our college days that modulus of elasticity of concrete depends on grade of concrete. The well-known formula is 5000 under root FCK. According to this formula, the modulus of elasticity for this M25 grade of concrete will be 5000 under root of 25. That will come out to be 25,000. Enter the same in the box. Here do keep in mind that you have to always see and change this elasticity value for your concrete as per the grade that you provide or choose for your project. Do not leave this value as by default. Your structural model strength will get affected a lot. Last thing remaining is to set the FCK value of this concrete. So click on this property modify button. Here provide the FCK value as 25 Newton per mm square, which is same as megapascal. Click on OK 2 times to finalize the changes. Now we will create a M35 grade of concrete material as well. For this, select this existing M25 material and click on Add Copy button. Change the name to M35. Elasticity value will be 5000 under root 35, resulting in 29,580. Enter the same in the box. Change the FCK value to 35 by clicking on this Modify button. Save these changes by clicking on OK button. Here you can see M35 concrete material has been added to the list. I will tell you in few minutes why we are creating M35 grade of concrete for a simple 5-story project. It's time to define grade of steel rebar. For this, select this by default steel property provided by ETABS GR60. Nowadays, we as a professional engineers are providing minimum of TMT 500 bar for any kind of construction activity, no matter how small the project is. From now on, you should not use 415 or HYSD 500 bars for your project. Always go with thermomechanically treated bars called as TMT. Compared to HYSD bars, they provide good ductility with strength as well. We have discussed a lot about these bars in our mega advanced courses. Now we are going to provide TMT 550D bar in this project. As compared to TMT 500, this 50 value extra strength will reduce the building steel requirement by 5 to 6%. More on this concept in advanced mega course. Name it TMT 550D. Here, as compared to the modulus of elasticity of concrete, the elasticity value of steel bars does not change much with grades. So leave this by default value as it is. We are interested in providing the grade of steel, the Fy value, so click on this property modify button. As this is an 550 minimum yield strength steel, so the Fy value will be 550. Enter the same. Generally, the tensile strength of bars are 50 to 80 points higher than its yield strength. So enter 600 in the FU bar. Here keep in mind that you have to send bars to a testing laboratory so that you get exact yield and tensile strength values like this. I have seen from my experience and various lab results that these local bar companies bar are never up to the level as described on them. Usually if a bar is of 500 grade, then the yield strength will come out to be 450 or 460 only. So try to stick to good company rebars only, like Tata Tiscon, SAIL, JWS Steel. Here you can see these extra FYE and FUE values are provided by ETABS. These are generally used for non-linear analysis. You can provide a value of 1.1 times the above values like this as per ETABS manual, or you can leave it as it is. Once done, click on OK twice to save these changes. As our materials are now on point, so we can move forward to define our beam, slab and wall section. Come to the define menu, then hover onto section properties, then click on frame section. Here you can see ETABS has created the column section automatically for us as per the beam column plan layout. We are interested in creating beams, so select this by default beam section and click on modify property button. Generally for commercial building having a span of 22 feet between columns, we provide at least 2 feet deep beams. So the final depth of beam after subtracting the slab thickness of 6 inch will be 1 feet 6 inch. In local language, this 1 feet 6 inch is called as lattice. For residential project where the span is less than 18 feet, there you can provide 1 feet 6 inch deep beams. Here change the name to CCBM 1 feet by 2 feet. The grade of concrete will be M25. Enter the depth value as 2 feet and width value as 1 feet. To check the clear cover and rebar properties, click on show rebar button. Make sure the design type should be selected as beam. Rebar material is TMT 550D, which is what we want. Now comes the cover. Here you can see if you read this line, cover to longitudinal rebar group center. From this line it is very evident that it is not a simple clear cover thing. Here we have to enter the actual distance between center of main bars to the outer face of the beam. So this is how we will calculate it. 25 mm clear cover plus 8 mm shear bar plus center of main bar. Generally maximum dia for beam is 25 mm. So it will be half of 25 mm, that is 12.5. So the final cover value as per ETABS requirement came out to be 45.5, say 46 mm. So enter the same in the bottom bar as well. Here keep in mind that do not make a mistake of entering clear cover value of 25 mm here. ETABS then will calculate the effective depth of beam completely wrong. So always enter the centroidal distance. We are good to go, so click on OK button twice. Here you can see the modification has been done. Now for this large span corner area where the beam length are varying from 25 feet to 30 feet, we have to provide at least a 2 feet 6 inch deep beam. So for that select this beam property and click on add copy of this property button. Change the name to CCBM 1 feet 6 inch by 2 feet 6 inch. Grade will be M25 and provide a depth value of 2 feet 6 inch and width of 1 feet 6 inch. Time to check the rebar and cover properties. Design as beam, rebar as M25 and a cover of 46 mm. Seems good. Click on OK twice to create the beam section. We will create another beam section for supporting the balcony boundary wall. Select the 1 feet beam property and click on Add Copy of Property button. Change the name to CCBM 9 inch by 1 feet 6 inch. Provide the depth value of 1 feet 6 inch and width of 9 inch. Check the rebar properties. All seems good. So click on OK twice to create this beam property. Our beam section has been created successfully. Now let's make changes to the column properties as well. Select this FSEC1 property and click on Modify button. Here you can see that this is our front corner circular column. So change the name to COLCIR1. Here now the most important and practical thing to learn would be about the column grades as compared to the beams and slabs. As some of you might be knowing about the beam column capacity ratio check and a joint shear check. In order to pass these checks, ETABS put a lot of steel in columns as compared to the beams. So the columns always remain stronger compared to beams. As we know that steel is quite expensive as compared to the concrete. For example, a simple 2 rods of 25 mm dia bar in a column costs the same as concrete required to fill up the entire column. Not only these checks increase the steel in the column, they also prompt engineers to increase the size of the column so that steel quantities can be brought down. So how to overcome this problem of high steel in columns due to these checks? The simple trick is to increase the concrete grade of columns. As columns are always casted separately from the rest of the structure, we have the liberty to increase the grade as per our own will. There is also an upper limit to this as well as per ACI codes. Column grade can be 1.5 times higher than the beam and slab grade. So 25 into 1.5 comes out to be 37.5. So roughly we can provide a M35 grade to our columns so that we do not receive unnecessary high steel in columns. And our beam column joint pass the capacity ratio and shear check as well without an increase in steel. I have talked about these checks in much more detail in our advanced mega course ETABS and RCDC lectures. We have also performed the manual calculation checks for these. Refer Field Ready website for more details on these courses. Provide M35 grade to this column. Time to check the rebar for this column. Click on Show Rebar button. Here the design type is column, which is OK. The rebar material is TMT 550D, which is what we want. The column configuration is circular, that is what this column is. Confirm bars will be ties, not spiral. The column has to be designed, not checked. Here you can see this time the ETABS provides us the option to enter the clear cover to this column. We provide clear cover to columns of 40 mm and the same has been provided. Rest of the parameters are not important, so you can leave it as it is. Save the changes. In the same way, change the grade of rest of the columns. Select FSEC2 and modify it. Change the name to COLREC2. Change the grade to M35 and save the changes. Do the same with the rest of the columns as well. Close the window by clicking on OK button. As our material and RCC sections are defined, now we are ready to provide beam properties to these null lines. To select the null lines, come to the Select menu, then hover on to Select, then click on Object Type. Select the null lines from the list, then click on Select button and then on Close. Here you can see all the null lines has been selected. Now unselect this front 3 large span beams. then unselect this ramp secondary beam, then unselect the staircase side beams. Now we can assign the 1 feet by 2 feet section to these selected null lines. To do so, come to the Assign menu, then hover onto Frames, then click on Section Properties. Here select concrete beam 1 feet by 2 feet, then click on Apply and then on OK. To see the beams in 3D viewport, click on this Extrude toggle button, selecting the 3D viewport. Here you can see the beam properties to the null lines has been assigned correctly, and our outer edge beams are now flushed with the column face as well. In the same way, we plan in AutoCAD beam column plan. Focusing on the plan view, now select the front corner 3 null lines. We will provide here 2 feet 6 inch deep beam. For that, come to the Assign menu, then hover onto Frames, then click on Section Property. Here select 1 feet 6 inch by 2 feet 6 inch beam and assign this property to these null lines. In the same way, without closing the window, select this ramp and staircase side beams null lines. This time select 9 inch by 1 feet 6 inch beam property, as these beams will only be supporting the walls above it. Assign them to the null lines. Now you can refresh the 3D viewport to see all the beams property has been assigned to the null lines. This is how you can create complex shape beam layout in ETABS within few minutes with 100% accuracy. Before we move on for creating slabs and shear walls, a necessary habit that you should develop as a professional design engineer is that you should check the stability of beam column portal frame. It is very important to know early on which beams are falling, which are not supported by columns. Once the slabs and shear walls are placed, you will not be able to see which beams are falling, as it will be supported by slabs, and it will lead to miscalculation of loads. So straightforward, hit the analysis button to check the stability of this portal frame. Here you can see clearly the front and back beams are falling, that by a large margin of e to the power 16. We were expecting that these beams will fall as they were at an offset from the column center. So break the analysis. Now the way ETABS understand how to support beams on a column is that whenever in the structure, if the beam is placed at the center of the column, then ETABS will rest that beam on that column automatically. But if it is an offset, then it will consider it as if it is hanging in the mid-air. In reality, from these photos you can see all these beams are at an offset from the center of the column. These pictures are of a G+12 story building beams and columns. So in reality, majority of beams can be at an offset to the column. So in order to tell the ETABS that these beams are actually lying on this column, we will take help of links. Links are objects that will help us to connect these beams to the column center. So first we have to define links. For this, come to the Define menu, then hover onto Section Properties. Then click on Link Properties. Modify this by default link property. We are interested in simply connecting beams to the column, so select Linear from the link type. I have explained what will happen if you do not provide beams at an offset much more in detail in our advanced mega courses with links types as well. Coming back, as we want to fix these beams, we will click on Fix All button. Click on OK twice to confirm these changes. Zoom onto this right hand side front column. We will connect these beams lying at an offset to this column through links. For that, come to Draw menu, then click on Draw Link tool. Click on this beam first and then click on the column center like this. Do the same with the other beam as well. This is how we connect beams which are at an offset to their respective columns. If you are not able to snap links to the column center, then you can come to the Draw menu, then click on Snap Options. Here make sure joints, line ends and midpoints are ticked. Click on OK to make changes. Continue scroll up and connect these two beams as well with single link to the column. In the same way, keep on connecting the beams to the respective columns. We will not be connecting these central beams as these are already placed at the center of the columns. Once all the beams are connected to columns, we will now define and place shear walls for lift here so that these beams are also supported. Come to the Define menu, hover onto Section Properties, then click on Wall section. Modify the property of by default wall by clicking on Modify button. Name the wall as Wall 6 inch. The wall concrete grade will be again M35. Here do keep in mind that retaining walls should be casted in higher grade of concrete, as higher grade of concrete tends to resist water seepage quite well as compared to the M20 or M25 grade concrete, costing a little bit more money, but it will increase the basement wall life as well as water tank life to a great extent. The type will be shell thin. I have already taught about all these shell types in our basic and advanced ETABS courses. We will not discuss it here again. Generally, we provide a 6-inch thick shear wall for buildings up to G+6. So provide a 6-inch thickness to the wall and click on OK to save changes. Click on Draw Wall Tool command. Here make sure that in the property box, the wall 6 inch is selected and the auto pier option is set to yes. Piers in ETABS have a similar meaning like columns. It is must to provide a pier label to each shear wall in ETABS, otherwise it will not design that shear wall for us. So choosing an auto pier option helps us to name the shear walls automatically. I have discussed this concept much more in detail in our advanced courses. Then click on the start and end point of this shear wall. If you are not able to snap to the line, then open the snap setting from the Draw menu. Here select the intelligent snap and architecture layer option as well. Here you can see now we are able to pick the points. This is how the shear wall center line reference helps us to quickly draw shear walls at correct location with 100% accuracy. Let's quickly come to the base floor. Select all these joints, as these columns in shear wall will get attached to the raft foundation, so we will fix these joints to form a rigid joint. For this, go to Assign menu, then hover onto Joints, then click on Restraints. Here we will fix all the translational and rotational degree of freedom of these joints. Click on the first icon to fix all the joints and click on Apply and then click on OK. Quickly select on the Analysis button to run the analysis. Here you can see this time none of the beams are falling and we got a deflection of only 0.7 mm. If you do not want that later on, when you reach to the top 5-story level and then you encounter structural instability message from ETABS, then do make a habit of checking the structural stability at each floor level before placing slabs on it. This will help you to avoid mistakes at an early stage. Break the analysis. It's time to create the retaining wall for basement. Activate the Draw Wall tool again. Make sure 6-inch wall is selected in the property. This time also, the auto peer option should be set to yes. Now, as we know that our shear wall will be aligned in such a way that its outside face will be in the line of outside column face. If we zoom in and look closely, here we can see that our beam center line is at a 6-inch offset to the column outer face. As our wall thickness is 6-inch, so the center line of wall will be at 3-inch offset to this beam center line. So enter 3-inch, that is 76.2 mm in the offset box here. Start drawing from top to bottom like this. Here you can see that our shear wall is perfectly aligned to the column outer face. In this way, our structural model is modeled as it would be constructed on site. Continue forming the retaining wall from one column to another in a clockwise fashion like this. Once done, right click to end the wall tool. This is how we create proper retaining walls for a building in ETABS. Now the time has come to create the slabs for this basement roof. Let's define our slab first. Come to the Define menu, then hover onto Section Properties, then click on Slab Sections. Here, select the by default property Slab 1 and click on Modify button. Change the name to Slab 6-inch. The grade will be M25. The shell type will be shell thin, as these RCC slabs, which are less than 1 foot thick, act as thin shell only. More on this in advanced mega courses. Generally, for a span up to 24 to 25 feet, we provide a slab thickness of 6-inch. It is a general rule, but if the load is more and we are getting slab deflection more than that specified by IS 456 code for serviceability, then we will later on increase the depth after analysis results. So as of now, provide the thickness of 6-inch, save the changes. We are going to create another slab for ramp. So select this 6-inch slab and create a copy of it by clicking on Add Copy button. Name it slab 8-inch. For ramps, we generally provide a thickness of 8-inch so that heavy loaded vehicle can pass through it without undergoing much deflection. Change the thickness to 8-inch and save the changes. We are done defining the slab section, so click on OK to save the slab list in ETABS. Let's start creating the floor slab using the point-by-point slab creation tool. Select it from the left-hand side toolbar. Change the property to slab 6-inch. Start making the central span slab by clicking on the column center to center like this. Once done, right click to end the formation of slab. This is how we can create custom size slabs in ETABS. Wherever you get the chance to support the slab at column center, you should take it. Same goes to the shear wall joints as well. Keep this area open for vehicle going downwards. Keep on creating the slabs from point to point, supporting them on column center and on shear walls if applicable. Now it's time to create ramp. The bottom of this ramp will come up to this beam. So we will copy paste these beams to the base floor so that they will act as reference point for us. To do so, select these beams, then come to edit menu, then click on replicate tool. Come to story tab and then select base level where you want to copy these beams. Ramp will also need support of beams to the left and right side of it. So let's create the inclined beams. Activate the beam draw tool. Select the 9 inch by 1 feet 6 inch beam section from the property list. Then come to the 3D viewport. Rotate the view to see the left hand side of the ramp. Pick the bottom point first, then click on the top point like this to create the inclined beam. And the same way, create the beam for the other side as well. Let's create the 9 inch by 1 feet 6 inch column here to support this above intersecting beam and ramp as well. For this, come to the define menu, then frame section. Here select the column 2 and create a copy of it like this. Change the name to CC column 9 inch by 1 feet 6 inch column. Provide a depth of 9 inch and width of 1 feet 6 inch. Save the changes. Activate the quick column draw tool from the list and choose our 9 inch column from the list. Now if you hover onto this joint in the plan view, then you can see that it is not aligning to the ramp beam direction. So let's rotate this column. Enter a 90-degree rotation value in this angle box. Now this column is aligned along this beam. Click here to create this column. Fix this joint bottom as we did before with the help of restraint tools. Let's now select these inclined beams and their respective supporting columns. We have to divide these columns at the intersecting points so that ETABS support these beams on this column. For this, come to the edit menu, then hover onto edit frames. Then click on divide frames. Here select the break at intersection option and click on apply and then click on OK. Here you can see both the columns are now supporting this beam. Now it's time to delete these reference beams. We do not need them any longer. Fix the base joint wherever necessary. Run the analysis to check the stability of these beams before creating slabs. Yes, these beams are now supported by these two columns. Break the analysis and click on point by point slab creation tool. This time select 18 slab from the list to handle the heavy vehicular loads. Start picking up the bottom side ramp points and complete the slab formation. Then go on for upper side ramp slab formation. Let's provide some meshing to these ramp slab. Select both the slabs, come to the assign menu, then hover onto shells. Then click on floor auto mesh option. Here select the mesh object into 3x3 elements. Click on apply and then on OK. Here keep in mind that we will learn about meshing in our analysis lecture of this series. Run the analysis to check the stability of this ramp element. Here you can see our ramp slab is well supported on these beams and these beams are well supported on these columns. The slab is only receiving a deflection of around 1 mm. Here ETABS is only exaggerating the deflection shape too much. Do not get confused by the deflection shape that it is deflecting too much. Later on in our load application lecture, we will apply the vehicular loads on this ramp as well. We are done with our basement structural modeling. As this lecture is getting lengthy, let's create the ground floor and above story structural model with water tank in the next lecture. See you in the next lecture.